Yeah, we are welcome back to the class this morning. So we are going to continue with and hopefully finish the aspect of performance measure for the aspect which we refer to as the evaluating machine learning models that we started a couple of weeks ago. We've covered much. We started by describing some of the possible ways by which we can evaluate our models, starting with the data partitioning approaches. So where we mention the possible partitioning, so which were basically divided into partitioning into what we call the leave one out. So, what we call number one is the holdout method. And the second type is what we call the cross-validation method. So which each of them subdivided into parts. In the holdout method, so we can have what we call division into just two. So which is called, usually this is the commonest and this is the popular one among people. We call it training and testing set. You divide your data into training set of maybe 70% and 30% for testing. So, however, you can also go further, especially if your data is sizable, you have a little bit big amount of big data, a sizable amount of data. So you can divide into three. So you're going to have the training set, then you're going to have the testing set, and then you're going to have finally the validation set. So that during the development of the model, you use this for training while testing to be sure everything is fine. Once everything is finalized, then you take this one, a totally reserved one, and then you can use it to judge the final capability of your model. It should be noted that for both this and this, they are not used for training the system. And that is why this method is equally acceptable. It's equally acceptable, just define the training and testing. So, however, like I clarify, there are a couple of people who so much believe in this option, and sometimes they could go fanatical about it. I mean, they don't want to see any other thing aside dividing into three. But that is not correct, actually. It is valid to use training and testing. It's okay. It's acceptable by a very big community of machine learning experts. But however, if you have enough data, of course, it's like in software engineering. When you develop a software, you test it within your company. Then when you are going to deliver it to the client, you also test it with their new data. See? So some people call it on-site testing or thereabout, just to increase the reliability or the confidence of your client on what you have developed. So this is why this is very good if you have the capability and your data size allows for that. However, if your data size is not big enough, you can go for just training and testing. And that is also good. You use training set for training, like 70%, it could be 80%, it could be 65%, it could be any percentage you choose. However, it's better to have more training set than the testing set. This is usually because, like we discussed, inductive learning hypothesis that the more, if the data is exposed to enough data and is able to perform on that enough data, then it can perform on unseen data set, which is the basic principle behind the idea of training and then testing model to predict what it has never seen before. So either you divide into two or you divide into three. These are all referred to as holdout method. Holdout method in the sense that you expose the machine to the algorithm to a side part of the data set while you are holding out some part of it secretly so that it doesn't see it. Later you can check if it can recognize it. However, the cross-validation approach is usually used for kind of a proof of concept, especially if your data set is very small. Sometimes you have very small data set. Imagine somebody having 16 samples, only 16 samples. We face this challenge in some engineering application where getting data is so difficult. Some experimental-based system also where it takes them maybe weeks before they can get few number of data samples. So in that case, dividing 16 data sample into 70%, 30%, it's going to leave you with very few data samples. In that case, people go for cross-validation. You see, we also discussed this, so we can refer to our previous videos. So like evaluating machine model 1, 2, 3. So because this is going to be the fourth one on it, and hopefully we're going to be finishing it today, inshallah. So therefore, when your data set is not enough, then you are encouraged to go for cross-validation. And then the cross-validation, it can be tenfold cross-validation, where you divide your data into tenfold, or it could be fivefold. So it could be threefold, as you wish. So the lesser the number of data you have here, the lesser the number of partitions you should use. However, what has been noticed based on research coming from one of the reviewers who requested the student to try that, he said your data is not much, why are you using tenfold? He said you should use threefold. So then the student went ahead and repeated the experiment using threefolds. Then we realized that the differences are not really much. You see, so that means it's not really a big deal when it comes to that. But it's not an option. Cross-validation method is not an option you go for if your data is big. Because one, imagine having like 20,000 samples and you try to go for cross-validation. There's no need to do that because it's going to take a lot of time to divide those data to 10 times and keep, because the idea is when you partition into 10 folds, so you're going to be using the first 9 for training, the last one for testing. This one become part of the training set. You take this one out for testing next time. So every fold will be used for testing at least one time. So you're going to be doing training and testing multiple times. So if your data is big, it's not advisable to use it. This is one disadvantage of it. And the second thing also is, if you develop a machine learning model using cross-validation, you can't deploy it for your client. It's not deployable for your client because this is just like a proof of concept. We want to check. If we get more data, maybe your client gave you like 16 samples, I say, oh, this data is very difficult to get. But can you just check if it's going to be good so that we can spend money to get this data? So you try to use those 16 samples to develop machine learning model using the principle of cross-validation. Then you see the idea that, oh, it's getting very good results. Even though very few samples, we're able to get like 90%, 85%, 95%. So it means you can encourage the company to go ahead and spend money to get a lot of data that we are going to develop the final model for you, then you can use it in your future prediction. So if they are able now, they are convinced because of the initial result from this cross-validation. So then they can go ahead, they get motivated to spend money to get a lot of data for you. Then you now use hold out method to train model with enough data, test the model, and possibly validate it again. Then you can deploy the model for them, and they can start using it in their future prediction. So this is why we say that cross-validation is often for proof of concept in most cases. But however, so as researcher, you see some researcher who want to see, and we would like to see how it's going to perform in the cross-validation. It's okay. In that case, some people do the two in their research. They will do hold out and they also do cross-validation, and they put the result there for people to see. That saves you having to go back if your reviewer decided to say, no, I need to see this. But however, the rule of thumb is if your data set is big, then you go for division into 3. If the data set is big, but not a little big or to some extent, then you go for just dividing into 2. But it's really very few samples, you go for cross-validation, because dividing into 2, holding out something is not really that reasonable because the data is just too small. Now, so we discussed this in our previous videos. This is called how do you partition the data? Well, that's okay. Once you know how to partition the data, then what do you check as you are building the model? We said you're going to check, once you train in the model, you want to check if the model is performing. So what do you check for? So that made us to describe last week performance measure for classification models. That for classification models, most important of them, you need to check your true positive, false positive, true negative, and then false negative. That is, how is your model performing? So if my model is getting 99% accuracy, we say it's not enough. You need to check your confusion matrix and see, is it really predicting the way it should be? So we said if we say false negative and false positive, they are the problems in your predictive solution. They are errors. But we say the errors, The implication of this error varies from one application to the other. For medical application, we explain extensively, and we refer us to our previous video, the part 3, where we made us realize that false negative is a no-no in medical prediction, because you are going to be saying somebody who is sick, your machine learning model will be predicting him that, no, you are okay. So the person will go home and try to enjoy himself, do everything every normal person does, only for him to run into complication in that disease. So that's why false negative in medical application is a very bad mistake. So if you have a machine learning algorithm that is having 95% accuracy, even 98% accuracy, but the only 2% error is coming from false negative, then we have another one that is getting 97, 96% accuracy, but the 4% error, they are all coming from false positive. So we are going to go for this. We are going to reject this because this is medical application. Because this one, the mistake here is that somebody who is not sick, but machine learning is saying the person is sick. So they will recommend the person for further follow-up in the clinic. On getting to clinic, they will run a further test and they'll say, oh, you are not sick. I think everything is fine with you. Sorry for the mistake. That was a mistake from our system. So at least you can go home, relax that, oh, alhamdulillah, I'm not sick. So of course it's a mistake we don't want because you might make some people to panic. Yeah, sometimes you make people to panic, but then it's just a temporary panicking, you know? So you panic for a very short period of time and then you get good news that you are not sick. You'll be happy. However, this guy who is actually sick, but has been predicted that you are okay, he will not even bother to come to the clinic. He will go home and start doing everything normal until maybe one day he just collapse. Maybe he had very high blood pressure, but the system missed it during the initial random checking using machine learning. So we discussed this extensively last time. So once you train your model using the training set, we also check the performance on the training set, but that's not our concern. Our main concern is what is the performance on the testing set that you are hiding away from the system. So you check the testing set and check for this thing I'm explaining. The mistake on testing set, is it coming from false positive or false negative? So if it is getting 98%, but all the mistake are the very costly one, we reject it. We go for lesser accuracy with mistake coming from less serious parts of the mistake. And we also explain that if we are dealing with production companies that produces some product and send it to their customers, then the reverse is going to be the case. In such company, they can afford to have a mistake of false positive, sort of false negative, but they cannot afford to have false positive. You can see in medicine, in medical application, false negative is no, we don't want it. False positive, we don't want it, but it's manageable. However, in production companies, depending on the way you are developing your product for, your software for, false negative is manageable. You see, false negative is manageable. For false positive is no. They cannot afford to have it. Why? Because false positive is going to predict that this product is okay, even though it's not good. Then they will send a very bad product to the customer, who will get it on delivery and go to Facebook, Twitter, and start advertising the company negatively, that this company is bad, they send bad product to them, this, and that. So rather, they don't want this kind of mistake, false positive. They would rather can accept false negative. False negative means a product is fine after the production process, but machine learning systems say, no, this product should be checked again. It's not good. So another quality control man, human being, physical employee will now check it again, since machine learning is saying it's not good. But then he now realized that, oh, this is a false negative error. It's actually good. So you are going to waste a little bit of human manpower to double check before sending to your customers. So this is called false negative, which is acceptable in the case of production processes because it put them on the safer side so that they will not run into trouble of customer discontentment. So what is good in production processes, medically, it is not acceptable. So that is why it is not just everything is yes, everything is no. So we have to understand the area you apply machine learning to be able to know the kind of, we call it the cost of misclassification in that area that you are dealing with. So you are dealing with industry, you are dealing with educational prediction. Which one should we pay attention to? You say a student is going to fail. Meanwhile, it doesn't fail. Or you say a student who might fail is not going to fail. Which one is more challenging? Which mistake can we manage? Which one is a no-no? However, false negative, false positive, they are both mistakes. But one of them is more costlier in some field compared to the other. So we describe all this in our previous setting. We also show us how we can compute the accuracy, which is the most important. It's very common that people use, but then it's not enough. That's why I give this example. You could be getting accuracy of 98%, but the mistake are coming from false negative. For medical application, it's not okay. So rather, we go for 96% accuracy with 4% error, but coming from less costlier side of the mistakes. So sometimes we have to go deeper to some of the actual performance measure of our system to be able to see what is the best approach to use. We also discussed the concept of confusion matrix from multi-class. The one we describe here is just two-class problem. We have positive and negative. You're predicting somebody has a particular disease or not. Or sometimes we have more, like when you are trying to recognize character, like English character or Arabic character. So you have almost maybe 20-something alphabets, sometimes in some languages or even more. So in that case, we call them multi-class problems. So we do that also. So you can see here how many DNA are misclassified into these. So the diagonal lines are always showing the positive, the correct one. These are the correct classifications, classified number of samples. Every other thing you see here, they are wrong because this is DNA classified as ER. See, this is TUB classified as ER. So, and also of other. That is for multi-class problem. And another one we mentioned also is that the more the number of classes, we can deal with that later on when we talk about classification algorithms. The more the number of classes, the more challenging getting accurate result becomes. But then it's still manageable. That's why binary classification problem is usually the initial one and very common one. Even sometimes you have multi-class, you can break it into binary classification problem. For example, support vector machine cannot solve multi-class problem directly, but it has a way of doing that. It breaks it into binary, and then solve it, or one against odds, as we are going to discuss when we discuss support vector machine procedures. So we give example on this false positive, false negative, and also for others, how we can determine if this is false positive or this is false negative. So everything was discussed last week. So and then we move to other areas of metric for performance evaluation. So we discuss the concept of, we say that accuracy is not just enough. That's especially if the data is not balanced. If you have an imbalanced data, then you might need to go beyond just accuracy or any other measure. So we can use precision recall curves. So we said this measure is usually needed when the class are very imbalanced. When we say class is imbalanced, it means, let's say you have 500 samples from your data. Out of the 500 sample, 100 are diabetes patients. Diabetes patients are just 100. The remaining 400, they are non-diabetes patients. This is called imbalanced data. You can see the number of sick person is far less than number of healthy person. So when you train with this kind of data, the system will be biased towards the 400 guy. That's why in that case, you could be getting good results in accuracy, but however, your machine learning is not able to recognize the sick person. As an example, we give just shortly, we give this example that just imagine this. You have two class problem, but class 0. So class 0, which means LD patient, is 9,990 samples. Whereas for class 1, which is the sick patient, the sick people, they are 10, only 10 out of 10,000. So now when you train a model like this is seriously imbalanced data, serious imbalance. Now, so even let's say you might have you have a situation whereby when you run the testing set converted all the data, predicted all the data to be class 0. You see, class 0, everything class 0, class 0, class 0. So in that case, out of the 110,000, 9,990 will be correct prediction, because this is the number of people that are not sick ordinarily. The remaining 10 that were predicted as class 0, even though they were class 1, will be the error. So when you calculate 9,990 divided by 10,000, you're going to be getting 99.9%. So you're getting 99.9% accuracy. So you might start jubilating that, wow, I've done a great job. But we say, no, you don't jubilate. Your model has only succeeded in pushing everybody to be one class. So it's not able to differentiate between class 0 and class 1. So such model is not good. Although you may see 99% accuracy. And this is one of the reasons why accuracy is not enough for you to just get accuracy and you start celebrating. No, you might have to go to your confusion matrix, as I've explained, see what is the false negative, what are the false positive. Because what this guy will do is he will put everybody here. See, he will put everybody here that everybody is here positive. You are positive. That's going to be the procedure. It's going to be 9990 here and 10 here. Everything on the positive side is 0 is 0. Nobody is going to be here. So in such a system, this is a very big error. And to you, because you are looking at only accuracy, you could be celebrating, thinking your model is doing fine. But no, it's not doing fine. So let's pay attention to that. That's why we need to check other metrics for measuring the classification accuracy, like the confusion matrix or the one we call the precision recall curve. They are all there in our system. Once you finish your modeling, you just click to show the curve. It will show you for that result. Then you can see the curve. So we discussed this. Other one is also called the ROC, receiver operating characteristics, also there. So it's very popular. So once you have the ROC, you have the area under the curve that could be calculated for you. So the area, this is called AUC, area under the curve for ROC. This one is going to show you a particular number, and they have interpretation. If your ROC, once the curve is shown to you, it will show you the area under that curve. If the value is equal to 1, you have a perfect prediction. 0.9, excellent prediction. 0.8, good prediction. Add anything up to, this is at 0.6, it is poor prediction. 0.5, random prediction. Anything less than 0.5 is totally out of place. So, but we don't want random prediction. So even though you might be getting good result to you, maybe 70% or 80%, but the ROC will show us that, okay, how is your system really performing actually? Is it really good in prediction? What is the probability that we use it again is going to work fine? Is it just a random system? So this is why we use other classification performance measure to check. We don't rely only on one. For example, this is an ROC. See, this is 0.5. The one passing through the curve here is 0.5. So the closer you are to this place, the better. If you can get something that is like this, if your curve is like this, it's passing through this and this. This one we call perfect one. You're going to have 1. The area under the curve, AUC, is going to be 1. But as you see here, this one is okay, but this one is better than 8. So the more closer you are to this particular angle, to the point that you are having perfect match with this, then we say, oh, this is the one we refer to as perfect prediction here, depending on the problem we are solving. So that's why, in addition to accuracy, confusion matrix, it's good to also to show your ROC or AUC, as the case may be. Let's say an example of how do we interpret ROC. So you can see here we have true negative, we have true positive. And this is the threshold between them. The ideal situation we are looking for is this. This is what I just showed you here. You can see this ROC. This is perfect one, 1. See, perfect one. This is perfect prediction. Everything is fine. That you are not pushing one class to the other. You are not pushing the other class to this place. You are well distinct. So, but when you see, this is when you have the AUC of 1. You can see true positive, true negative. They are distinct. You got all the true positive correct. These are the correct diabetes people. You also got true negative. These are the non-diabetes people. See, now you got them correctly. prediction. There's no overlapping. Everything is fine. So you're going to get an AUC of this, which is indicated like this. So when you get 0.7 AUC, this is going to be like this. You see here, you see overlapping. Your true negative is overlapping the true positive. So you have some mistake here. This is false positive. This guy is supposed to belong to this class, but you predicted it to belong to this class. This one is supposed to belong to this class, but you predicted it to belong to this class. So we call this false negative. Why we call this false positive? Because originally it's supposed to belong to this one, but you call it the other class. So it means you are making a little bit of mistake in this side and this side. So me looking at your area under the curve, if you tell me your accuracy is 96, and then I will see your AUC, I will understand that, oh, 0.7. Okay, it's not super as you think, because you are still making the mixture, you are mixing up things at the lower level. So, and then here you're going to have the ROC for such 0.7, depending on the problem you are modeling. So this is telling us we sometimes need to go beyond accuracy when we are modeling, when we are evaluating our models, to be sure we are actually having correct decision. We take the decision on the best system. And then we have another case. You can see here, area under the curve. You can see that this is the one I call the random. You can see that the true positive and the true negative are almost superimposing themselves. You mix things together, random prediction. Nothing is working fine there. And then you have the worst scenario. Worst scenario is this, where AUC is 0. It means you push all the sick people, you predicted them not to be sick. And you push all the people that are healthy, you put them to be sick. You see? You put true positive in the side or put true negative. You actually enter predicted. That is a very, very worst prediction you can ever have. So that's why once you have your accuracy, we also check which kind of ROC do we have, and then that will give you a little bit of what is obtainable. This is it now. So we said that if the difference between PRAUC and ordinary AUC is when the class is imbalanced, then we go for the PRAUC, whereas ordinarily the ROC is okay for everything. Now, finally, towards the end, we look into the performance measure for regression models. As we know, the supervised machine learning model we treat in can either be classification, where you want to predict yes or no, or you to classify things into different classes. Then what if here we have regression? You want to predict actual value. I want to predict the score of a student in an exam. Out of 40 marks, I want to predict what the student will get. So I go into previous experience in the teaching of the same course, and then I get previous data and try to predict what the present student might get. So in that case, you are predicting direct number. How you want to estimate the age of an individual. Or you want to predict the strength of material in the material engineering. So engineers, they know this. So this is called regression problem. So how do we measure the regression problem? We have various performance evaluation metrics for regression models. So, and often depends on the problem you are solving. So that's why you have to look at the literature and use the one that they are using in that literature, because if you are going to compare your work to previous work, then you must do it the way they used to do it. Otherwise, your comparison will not be valid. For example, I know if you want to do prediction for software engineering, I want to predict how many people, how many manpower effort that will be needed to complete a particular software. We call it software effort estimation. So there are special, apart from using root mean square error that we're going to mention, there are special formula they use also to judge the performance. So you have to check the literature to see, okay, what are they using here? And then you have to apply it appropriately. Because as we are going to see, there's no single performance measure that can show us everything. Even in the classification example we have demonstrated, sometimes accuracy can be giving you something unique, but down detail, you know that something is not correct. But you will not know by just checking the accuracy. You know when you check the ROC or when you check the confusion matrix. That is why we usually use multiple performance measures together at the same time when we are evaluating our model, in order not to be deceived by one. If one is deceiving us, the second one will reveal that, no, that guy is just trying to deceive you. So that is why we don't encourage people to use just only one performance measure. No, it's never done like that way. So you have to go deeper and be able to understand what is happening. So one of the very popular performance measure in regression problem is called the correlation coefficient, or the coefficient of correlation, as some people call it. So here's the formula. So here's the formula that is often used. So you have your prediction, you have the value, that original value that was given to you, then you have the predicted value. So you have the value that is given to you here. This is the actual value given to you minus the mean of the actual value. This is the mean. You can also write it this way. Actual value given to you minus the mean into bracket of predicted value minus the mean of the predicted value. So, and then you can see this summation, and then you do it together. This is going to be root, from where we have the root mean square error. So where we say YA and YP, they are the actual and predicted value. So you are comparing the actual value given to you with what the machine learning model already predicted for you. So we want to see how close they are. So correlation will show you how good they are or otherwise. So usually for a very good system, we expect a correlation of 100, which is going to be called, people call it 100%. So you're getting 90-something% correlation coefficient or coefficient of correlation, that's fine. But then you don't stop there also. We usually use root mean square error side by side. Root mean square error is one of the very, correlation coefficient and root mean square error, from my own experience, I don't know, the two very popular, unique to many fields based on my experience so far. So there are other measures we are going to mention, but these are two are very, very common. At least if you can use root mean square error, because it was going to show you the actual accuracy. How far is your prediction to the actual value you are given? Whereas this one is just going to tell us the flow. Are they flowing together? You know, correlation is if I'm moving in this direction and somebody is moving in this direction, we just want to see, are we moving at the same pace? So it doesn't mean we are very close together, but we are moving averagely at the same pace. And we could also have negative correlation. Of course, we don't expect that in prediction. Whereas somebody is going opposite you and you are going this side, but you are moving at the same speed. So your correlation is going to be higher, but it's going to be negative correlation. It could be minus 9.95%. It means as you are moving in opposite direction, the other guy is moving in the opposite direction, but you are moving at the same rate. So you have high correlation, but it's negative correlation, which of course we don't want it in predictive solution. Now, so that is why it's not reliable also to use only correlation coefficient to determine the accuracy. So you use root mean square error to support it. And that is, what is the value? This is the predicted value and the actual value. Subtract them, square them, do it for every value. You know, this is first sample. This is the predicted value minus, this is the actual value given, this is your predicted value. Find the sum. The answer was originally it was 40. We were predicting the mark of a student. The student was reported to have gotten 40 according to the data with us, but the prediction now is 38. So you subtract 40 minus 38, that is 2, and then square it, plus do that for every sample you are dealing with, and then find the average, and then of course the average divided by n, and then that's why we have the name root mean square error. It's actually the mean square error. Then we put the square root, which is why they call it the root mean square error. So this is going to show you how close are you to the actual values you are given. So we say other quality measures include but not limited to, we have others like average absolute percent relative error, standard deviation. Sometimes you want to find the standard deviation between the predicted and the output. You want to find how far they are together. So that's why if you use packages like Weka or any other software, you can select what are they. By default, it to show you root mean square error, absolute percent relative error, standard deviation. If you want more, you can go into the system, more option, and you can set to display more performance measure for me, depending on the area you are looking at. So these are other evaluation measure for regression: means absolute error, mean square error, mean absolute percentage error, mean percentage error, yeah, root mean square error. The one I would like to mention here, which I actually advise us to stick to using when you are dealing with regression problem, is the difference between the actual value and the model's estimation using plots and figures. This is very important. That it's not just, don't let your predictive outcome be only in numbers. Show them pictorially. Let me see how close is your prediction to the actual value that were given. That is showing difference between the actual value and the model estimate. This is very, very important. So the outcome is supposed to be 40, we predicted 38. Okay. But once you calculate the root mean square error, it's going to show me maybe it's going to 0.356. Then you compare with the previous guys who work in this area, maybe they were getting 0.6, which means in root mean square error, the lower the better, because you are actually trying to reduce the error. This is the essence of root mean square error. Whereas in correlation coefficient, you are trying to increase the correlation between the predicted and the actual value. So our aim here is to get as high as possible, up to 100% correlation coefficient. However, in root mean square error, the lesser, the better, because this is the actual difference between the predicted and the given value. So in order to make people to appreciate your output, so I encourage you to, in addition to those numbers, try to bring up a plot like this. You can see this is a sample cross plot between the experimental and predicted result for the testing phase. See, I mentioned the testing phase. People care more about testing phase or validation phase. Don't put up the result of, don't waste your time on putting up the result of a training phase. If you put it there, it's okay. But then to me, people want to see your testing phase, because you could be getting good result in training phase. Meanwhile, the testing phase is going to be bad. We call it, that's going to be called overfitting. So you don't celebrate result until you check the result of testing set. And that is why the default values you get in weaker package is the testing result. If you want to show, if you want it to show you the training result, you have to go to options and then select show me the training outcome. Then to show you the training result. Because by default, it's hidden, because they believe nobody wants to see your training performance. Something you have seen before, we asked it also to predict it. In most cases, they're going to predict it, but we are more interested in the extrapolation of the power, the extrapolation power of the model. How can it perform on data set it has never seen before? So once we have the testing phase result, this is the, you can see this is the correlation. Look at it. This correlation 0.9991. See, you can see the actual value. This is the model. This is your model now. This is the model line, the model you have developed. You can see very close together. Even though it's not touching all the points, but at least they flow in the same direction, almost touching majority of the points. See, so you plot the predicted value against the experimental value. By doing that, you have something like this. That will show you how your prediction is really working closer to the actual value. This is another example. You see, the comparison of experimental results and the existing model. You can see here. So you can see here. You have, when you develop your model, this is the experimental refractive index. This project developed a predictive solution for predicting the refractive index of deoxygenated blood. Another one work on oxygenated blood. Try to see the difference between the refractive index. So this is the proposed model, the new proposed model, and this was the result of the previous people work on it in 2016. So sometimes also when you are comparing results, you can put their, if you have their values in their paper, you can put it on your plot. You can see their own. This is the point. This black spot, they are the actual value given. So the new proposed model by our team actually achieved this one, genetic algorithm-based support vector regression model. You can see that the new model was actually passing through direct points, connecting them, showing how close to the actual value the model is actually, reaching almost near to 100% predictive accuracy. You can see. But meanwhile, look at the earlier guy here, the earlier published work, the one in this color, you can see it's also good, matching some point, but sometimes extending beyond it, sometimes extending beyond this, but at least it's a little bit also acceptable, but not as the new one, because that is the essence of the improved model that was proposed. So when you do regression prediction, it's always good to have something like this. Let people see how close is your model to the actual values that you have been given for the experimentation. So we call it, some people call it cross plots or the plot of the predicted over the actual given. So, and also of other method, the means absolute error, mean squared error, means absolute percent error, as I mentioned, that host of others that they are all there. So depend on the area you are modeling. So look at the literature there, select those they are used in the literature, and make sure those are the ones you are going to report, because you are going to compare. But in addition to that, I strongly recommend to you that make sure you have something like this that will show the actual value you have predicted, compare to the actual value you are given, or predicted value against the actual value, and host of others. And then, of course, few suggestions. These are just suggestions that people believe that if there is some of the analysis of each method, they say root mean square error, is it robust to outlier? They say it's not robust to outlier. Yeah, it's not robust to outlier because you are using if there's an outlier in your data, which means outlier, every data set are close here. There's one big data there. All the values are between 0 and maybe 36. And then we have one data that is 1 million in size. So, you know, when you calculate your root mean square error, it's going to take you out of the blue. So you'll be out of range, actually. This is the idea. So this is why, again, why people use root mean square error. It will show you that something is wrong with your data, actually. So mean absolute error, they say is, yeah, it could be the way it was calculated, because it used absolute value. It could actually have resilience against outlier. Mean square error is also there. The MAPI also has some resilience. So it depends on the problem you are solving. Check the literature and go for what are the established evaluation measures that they use in that area. Except you are the first one to work in that area, the first one to establish the idea of using machine learning to predict. Then you can come up with very robust one, try to see, but root mean square error should not be removed. Because we say it's not robust to outlier, it doesn't mean it's not good. No, it actually will show you that no, something is wrong with your data. Because the one that is robust to outlier, even though outlier is there, it will not let you know there's outlier there. It could be an advantage and it could actually be a disadvantage. So rather, put root mean square error there, put MAPI there, and then put MAE, mean absolute error there. Have like as many as for like 4 or 5, since you are the first one to start this new idea in that field of yours. However, check the literature to make sure that you are actually, otherwise try to stick to what has been established or improve more and explain why there's need to add more evaluation measure with very good justification. And finally, and last but not the least, irrespective of either regression or classification, it is highly recommended that our results should be presented also in very smart way in pictorial representation. Try to put your result in a very nice way that people can see it at a glance. Yeah, when you put in a table, you can try to match the 2-3 tables together in one plot so that people can see at a glance that, oh, this is the proposed method. This is root mean square error. You can see root mean square error. The best method is getting very low root mean square error, while this one is higher. But when it comes to correlation coefficient, the best method is getting the highest correlation coefficient. And then this one is getting lower correlation coefficient. See, this is why this is advantage of a kind of visualization. And then there will be a cap. You can do a caption here. The lesser, the better. For root mean square error, the lesser, the better. Whereas the higher, the better. So this will hopefully facilitate people getting clearly at a goal what was the outcome of your work. So with this is what we are going to have as far as the evaluating machine learning model and the performance measure we are going to use for those evaluations as may be appropriate. So thank you very much all for listening. So if you have any questions, so we can move to the question side. Thank you for the patience, and then looking forward again to see you.